Now go to the Hooke law, and we start with the review of the Hooke's law that we discussed when we talk about the axial load in the very first class of this lesson, the first week. So let's talk about the Hooke's law. For axial load. With that here, if we have axial load, so that for a member, and if we have applied a load, then the member, for example, in tension, the load in tension, then the member will be deformed, the length changing, and if it in tension, the member become increase the length, and the load P, and we have the load P here. And if we're talking about sigma, so if we have divide P over A, so equal to sigma, if you recall, and also here you have P over A equal to sigma, if we talk about the normal stress. And we also know how to define the longitudinal and lateral axis. This is the longitudinal axis, if you recall, and the one that transverse cut is lateral axis. So with that, if we assume elastics, then the Young modulus, or the modulus of elasticity that we already know, is E is equal to sigma normal stress over normal strain epsilon. And we also have what? The epsilon longitudinal along the longitudinal axis, the normal strain along the longitudinal axis equal to sigma along the longitudinal axis that we just saw here, sigma P over A, divided by the Young modulus. So basically just flip in the previous equation, E equal to sigma over epsilon. And of course, we also, with the Poisson ratio, if the longitudinal axis increase the length, the lateral axis will reduce the length, if you recall that, and it represented by the Poisson ratio for the Poisson effect. And with that, we have the normal strain in the lateral axis equal to nu, which is the Poisson ratio, epsilon longitudinal axis. And because, as I mentioned, if the longitudinal axis increase in length, the lateral it will be reduced. It can be the width or the thickness, so that's why it have a negative in front. And if we plug the both equations, so it will be nu negative, and then we have sigma longitudinal axis with the P over A for the axial load divided by E. So that is the Hooke law for axial load, and we already know that in the first week. And now let's move on to how about the biaxial load. So go a little bit more generalized, and then we continue with the generalized Hooke laws. So Hooke's law, now that is only one axial load. How about the biaxial? Biaxial load. So what do we have? If we have a block there, and if this block is in tension, for example, then you will see in all direction, then that block will increase the areas, or you can say increase in both the length in both direction, because biaxial load. So we have the stress in this is sigma x, of course the opposite side for equilibrium is the same, and we have here sigma y and sigma y there. So both sigma x and sigma y are in tension for my example here. Then if we assume homogeneous and isotropics, if we assume homogeneous, same material throughout, homogeneous and isotropic, same properties in all direction, isotropic. Then what we have? We will have modulus of elasticity in x direction, also same as the modulus of elasticity in y direction, even in the z direction, because that is the same property throughout, based on our assumption is homogeneous and isotropic. And of course the new, the Poisson effect, Poisson ratio in any direction, it will be the same x, y, and z. And of course we also have the shell modulus, or the modulus of rigidity, gx equal to gy equal to gz. So all the directions should have the same properties, material properties. And with that, as you can see, that we got Hooke laws for the biaxial load. How about the general load? Not need to be biaxial, it can be shear, 3D, etc. So that we call the last one, we have generalized Hooke's law. Generalized Hooke's law. So you will see the handout that we have in today's class in the lesson. So you will see handout, and I'm going to explain here without writing. The handout is available on Canvas. The first one, generalized Hooke's laws. What is that about here? And as you can see, there are two ways to use the left. As you can see, if the problem give you the stress, then you can convert to strain with the given sigma x, sigma y, and tau xy. You can be able to find out epsilon x, epsilon y, and also epsilon z and gamma xy with that equation, the first red blocks in there. And in terms of the principal strain, if the problem we already find out the principal stress, sigma 1, sigma 2, and when sigma 1, sigma 2, we don't have the shear stress in that plane, then you will be able to find out that in the second block on the left, as you can see here, epsilon 1, epsilon 2, and gamma max. And now that is typical in the real life, as you can see in example or worksheet 13a, when we have the strain and find out from the measurement, and we find out the state of strain block. And in here, you see from strain to stress. So if the problems that have epsilon x, epsilon y, or and gamma xy, then you apply the block here, sigma x equal to E over 1 minus nu square epsilon x plus nu epsilon y, and similarly sigma y, and you have tau xy. So if you want to find out sigma x, sigma y, and tau xy, if you draw the Mohr circle, just like the example I do in the Mohr circle today, Mohr circle for strain. You already find out epsilon 1, epsilon 2. You can find out the principal stress directly from this one, sigma 1, sigma 2, with that equation over there. So it normally we see in practice we normally measure strain in the field, actual structural member, and we find out stress either with these two block equation. It depends on what we have, whether we have epsilon x, epsilon y, epsilon gamma xy, and we want to find out sigma x, sigma y, tau xy, or we want to find out the principal stresses, sigma 1 and sigma 2. And to solve that for the problem in worksheet 13b and c, that is the process to solve. As you can see here, normally we start with the strain rod set data, something like we talking about in 13a, and then you apply the three equation, three unknowns. We will do that in worksheet 13a. We can find out epsilon x, epsilon y, and gamma xy, and that determines state of strain. That is nothing new. If you are not sure, go back to the worksheet 13a. And there are two ways that you can find out the final output, which is the principal stresses and the maximum in-plane shear stress, sigma 1, sigma 2, and tau max. How? The first, as you can see, the flowchart, the process on the left. The first, after you have epsilon x, epsilon y, and gamma xy, you draw the Mohr circle for strain. This is nothing new to you. See my example in the lesson note. You can be able to, from that Mohr circle, you can find out epsilon 1, epsilon 2, and gamma x. And then you use the generalized Hooke law, and you already have epsilon 1, epsilon 2, and gamma max in the Mohr circle for strain. You will use this equation here, these two equations, principal stresses, sigma 1 equal to E over 1 minus B squared, and then epsilon 1 plus nu epsilon 2, and we also have epsilon 2 equation there, and you can see it symmetrical, so you just flip 1 and 2 in the next equation. You get sigma 2, and that we can find out the final output, sigma 1, sigma 2, and tau max. And of course, the other way that after you find out state of strain, you can use the generalized Hooke's law, and the output is sigma x, sigma y, and tau xy before you draw the Mohr circle. So that is mean that you have state of strain, then you apply these three equations to find out sigma x, sigma y, and tau xy. And when you have those three, apply the Mohr circle for stress. You can draw the Mohr circle for stress in here, and that go back to the previous lesson, how to draw the Mohr circle for stress. And then from the Mohr circle for stress, we can find out the sigma 1, sigma 2, and tau max directly from that Mohr circle. So there are two ways that you can find out. And in the solution that I'm going to present for worksheet 13b and c, we use this route, which is determines state of strain with the three equations, and then we draw the Mohr circle for strain. We utilize or generalize Hooke's law to find out the output is sigma 1, sigma 2, and tau max. And I task you to practice that same problem with the other process on the right. Generalize Hooke's law, Mohr circle, generalize Hooke's law to find out sigma x, sigma y, tau xy, and then draw the Mohr circle for stress and find out sigma 1, sigma 2, and tau max. Both method, both way, both process will go to the same destination, which is 6.1, 6.2, and tau max. So with that, we're done for the lesson note today. Go ahead to practice worksheets 13b and 13c.